Hi, I'm Haris Kunari from Department of Physics, Aligarh Muslim University, Aligarh, India. Today I'll be presenting my talk on critical evaluation and compilation of atomic data. I'm very much thankful to the organizing committee of the conference, including Professor Ananil Hayas, for inviting me to deliver this talk. Here is the short outline of my talk, starting with introduction about atomic data and their needs. Then I will be explaining the methodology of spectroscopic analysis and its evaluation to some extent. And here I have taken two examples for the demonstration, the spectra of carbon atoms and the spectrum of triply ionized gold. Finally, about the ongoing works on different So here is the introduction. The accurate atomic data on spectral lines wavelength and their energy levels involved and transition parameters such as transition probabilities, oscillator strength and upper lifetimes of atoms or ions are always important to upgrade and update the Atomic Spectra Database ASD NIST. The ASD is widely used by astrophysicists, researchers from technological and industrial sides, and the theorists too. Astrophysics needs accurate atomic data from the laboratory. Reliable atomic data are also required for many applied researches in which any form of plasma is a part of. Fundamental interest is to test the different theoretical models. Here I am showing the atomic level data from ASD NIST. These are interactive figures which can be accessed using the link provided here. Different color schemes are used here to represent the amount of levels data available for each of these elements. The triangle on the right side is made up of several tiny square boxes. From top to bottom, the elements are plotted with increasing of their z, and on horizontal direction their spectra are given. Indeed, more data are available for low Z elements. As Z increases, only limited data are found for elements with higher charge states. In fact, only groundmost level is known for most of them. See the area filled in the dense green color. So here is the similar plot for atomic lines data from ASD NIST. Again, more data are available for low Z species. And for high Z elements with increasing charge states, no lines data are available. Exception applies to the spectra of molybdenum, xenon, cesium and barium and tungsten. In fact, molybdenum and tungsten composites are used for fusion reactor diverters. Note that most of the NIST data are critically evaluated by a dedicated person from the NIST. So the question is, why does NIST carry out the critical evaluation before publishing the data in ASD NIST? This is because of the problem with most laboratory data, irrespective of their types. The atomic data present in dissimilar formats. The data are widely scattered in the literature. On right, you see the number of published experimental papers on neutral carbon from 1900 to 2015. There are more than 180 papers. Then the question is how to combine these work, and what if they contain several values for a given quantity that disagrees greatly. So the purpose of critical evaluation is to combine all relevant data and evaluate them. Also filter out the accurate wavelengths to produce the optimized energy levels, establish a theoretical basis for the observation, and provide the transition probabilities for the transition wavelength involved. Here I am giving a brief methodology of spectroscopic analysis and evaluation of atomic data. It can be applied to any spectrum. At first, the motivation is to obtain high resolution spectra of the element of interest to various experimental conditions, then calibrate the obtained spectrogram and estimate its wavelength uncertainty. In next slides, I'll be explaining two types of spectrometry, one with conventional grating and other with modern Fourier transform spectrometer. A spectrum contains presence of lines from different charge states. They needs to be separated out. And if the spectra are recorded on different plates, each of them must be calibrated separately and then combined to build a broad line list. Next part is to identify the spectral lines, means finding of their lower and upper levels. This leads to obtain the energy values of the levels involved too. In this process, we often take the theoretical prediction, for example, HFR calculation from Kavan code into consideration. If observation and theory are consistent each other, then the substantiation of lines identification and energy levels are complete. When multiple lines are available for levels involved, their optimized energy values are obtained using a least square adjustment. Once optimized energy levels are available with their uncertainties, they are used to compute the accurate wavelength called Ritz wavelength for all transition involved or possible between these energy levels. If applicable, we do intensity modeling for the observed line intensity using Maxwell-Boltzmann equation, valid for an optically thin plasma under LTE state. Also, if sufficient data on a given spectral series is available, then they are used to the spectroscopic determination of ionization energy of that species. Here is the view of a classical high-resolution vacuum spectrograph of 3 meters size. It uses a triggered spark source for the spectral excitation. High vacuum inside the spectrograph is required since it operates in the wavelength region below 2000 angstrom. The spectrograph has high groove density, normal incidence grating, capable to produce a dispersion of 1.4 angstrom per millimeter. The spectrum is recorded on Kodak short wave radiation plates and they require calibration. Here I am showing a sample spectrum. It is for the element Sn obtained with the spectrograph shown above. 4 different tracks of spectrum are recorded here. This was done to separate out the ionization stages of different lines. For example, 2 strong lines of Sn3, Sn5 are shown here. The Sn3 line is appeared in all 4 tracks, but the Sn5 line appeared in only 2 tracks. This shows the bottom tracks are much clean in terms of the spectral content and favor the lower charge state as they are obtained with a low voltage spark. The spectrum on the bottom is also for Sn in ultraviolet region recorded on a Wadsworth instrument. Prominent lines of Sn2, Sn3 and Sn4 are visible on this plate. The spectral lines shown in red boxes are due to the impurities in the spectrum. They are often helpful for the calibration of the spectrum. As briefly explained above, the calibration of spectral plates are done with the help of best available internal standards, that is the impurity lines present in the spectrum. These are the common impurities present in the spectrum. Nowadays, we can use a flatbed scanner for the spectral measurements. So this slide is about Fourier transform spectrometers, which are known for their absolute accuracies. Though FTS has a linear wave number scale, due to the Korn's advantage using a stable helium neon laser to act as an internal sampling reference frequency, a small multiplicative correction factor must be determined from the accurately known reference lines of the buffer gas such as argon or neon or molecular lines present in the spectra. Here I am showing one of the example of calibration plot in which accurate wavelength of O2 lines are deduced with the help of the calibration of argon 1 4:4p lines. Total wave number uncertainty in FTS has two components. One major part is statistical uncertainty in measuring the line position, which is mainly due to the line width W and the signal to noise S/N ratio. And the second component is systematic uncertainty stemming from the calibration. So here is the equation to find out the systematic uncertainty. So as we described earlier, the calibrated line list carries spectral lines wavelength and intensities. Apart from energy interval matching, the important parameter for correct line identification is the line intensities and their agreement with the transition probabilities or GA values. See an example for the line identification here for SN2 5s/5p square quarter p to 5s/5p 5d quarter p 3 half level transitions. Since all three levels of quarter p levels are known, the upper energy level must be observed with three lines and their intensity must be also according to the GA values from the theoretical calculation. So here we see an agreement except for this line, which is a blended line. So after the correct line classification, all levels which are connected by two or more observed transition need optimization. A least square optimization code called LOPT is widely used for this purpose. Now we are going to few of the examples. So here I am using carbon spectrum and gold spectrum for the demonstration. So the question is why the spectrum of carbon is important. We know that carbon is ubiquitous in the universe and it is present in stars, in interstellar medium, and it is one of the major coolants for the interstellar medium. It is also one of the mostly common found impurity in the laboratory plasma. Also, large-scale atomic data on carbon are required for fusion plasma diagnostics. So here is the timeline of C II spectroscopy. You can see that the early investigation started in 1920s and the major investigation is in 1953 by Glad and Esberg in 1958. So all this data until 1963 has been compiled by C.E. Moore. So they are known as the Morse table. So after the Morse compilation, there are plenty of other work which are not included in the ASD or Morse table. So the goal of the present compilation is to combine all sorts of data in methodical way. So I have already explained what are the goals of the critical evaluation. I'll just skip it. So here is the spectral lines data of C2 in ASD NIST in its version 5.9. The primary data source for this data is Morse table. However, no data in this table has explicit information on uncertainty of observed or its wavelength. The lowest data for C2 are also from the Morse table. Again, no uncertainties for energy levels. Therefore, the spectrum needs a critical evaluation. So the question is, how do we start the evaluation of observed wavelength? We started the evaluation of wavelength with the comprehensive observation of C II spectrum by Glad in 1953. To simplify the task, the listed lines are categorized in terms of perturbations, line intensities, and other line characters. And each dataset were evaluated separately with its counterparts. A total of 450 spectral lines participating in 500 transition were retrieved with their uncertainties vary from 7 milliangstrom to 50 milliangstrom. Using these wavelength, the level optimization was carried out and all other measurements were successively added after their evaluation. So here is the summary of the entire analysis for C2 and the important results are summarized here. We have published this paper in this year. So here I have taken another example, the spectrum of neutral carbon for the illustration. Here you see the Gaussian diagram for carbon and its count configuration is 2s square 2p square with these 5 levels. The excited 1 electron configurations are of 2s square 2pnl, and the other excitations are 2s cube and 2s 2p square nl types. So here is the view of amount of published atomic data available in experimental category from 1900 to 2015. Again, one has to critically evaluate all of them so that a standard spectral data set could be procured and use those for various applications. In case of neutral carbon, its numerous spectra are available from FT instruments. One of the previous reported works of Wallace et al. Reported the FT lines extensively, but the problem is that they are not consistent each other. So we decided to carefully measure all the spectra, and here are the details of 5 spectra used for this work, and all the spectra were most vital for determining the energy levels with less than millicentimeter verse uncertainties. We have also added the accurately measured transition frequencies of forbidden lines within the levels of ground 2s square 2p square configuration. All these are added into the careful level optimization process so that stable levels are obtained. The other spectrum that taken into consideration is the IR spectrum of Sun, in which numerous absorption lines of neutral carbon are observed in these missions. All are the FTS based, but most of the lines are replaced from the laboratory measurements. So only remaining 74 lines are added to the global or level optimization process. So here is the list of UV works considered for the evaluation, and all these works are calibrated with precise Ritz wavelengths determined from the optimized energy levels. So in this work, we have also added additional lines emanating from the Rydberg levels. These lines are easily produced in a carbon-rich star. Apart from the bond-bond spectra, the bond-free auto-ionizing spectral data were also inserted into the level optimization. So here is the view of our obtained results on energy levels data with their uncertainties. A total of 435 levels are established using 1250 observed lines, and 500 lines are FTS based. So the advantage of the optimization is that we achieve a relative uncertainty for the new recommended energy levels that vary between 10 to the power minus 9 to 5 into 10 to the power minus 4. Here is the mapping of lines length versus the number of intensity observations. Some lines are measured 10 times and most of them have at least 2 observations. So the reduction of these line intensity into a common single scale is a non-trivial problem in the spectroscopy, as different observers uses different relative scales for denoting the intensities. Their light source and instruments are also different. So one of the suggested method is to carry out the intensity modeling for each of the observation using Maxwell-Boltzmann equation, which sensibly apply to an optically thin plasma under LTE condition. Here is an example of Boltzmann plot analysis made for C1 lines observed in an FT spectrum. The effective excitation temperature of the observation is derived after removing the wavelength response of the registration equipment. A similar treatment should also be carried out for all other spectrum. If line intensities are available from multiple observation, then their consistencies are checked and averaging was made. So to determine the ionization energy of neutral carbon, we use Ritz content effect expansion method, which employed for the experimentally known 2p NP triplet D3C. Our new value is 9 times more precise than the previous value. So here I summarized the major results of C1 spectrum. We have already published these results. So the question is that what data is still needed for neutral carbon? We need isotopic data on wavelength and shift. Now let us go to the last sample spectrum of AU4. We know that the elements beyond Z greater than 30 are synthesized via a neutron capture process such as S process or R process. So the neutron star merger events are a potential avenue for these R process events. So with the emergence of multi-messenger astronomy, surveillance on neutron star merger are now possible. One of the recent event detected in August 2017 detected both gravitational wave and the electromagnetic spectrum. So the heavy elements such as silver, gold might be created in these sites. So in order to interpret the electromagnetic spectrum, large scale calibrated atomic data are required for all high Z elements. So the calibrated atomic data for low numbers of gold are already available, but not for the AU4. So the AU4 spectrum was recorded on a 10.7 meter normal incidence vacuum spectrograph at NIST with the help of a sliding power source. The spectrum covers in this wavelength region with a dispersion of 0.8 angstrom per millimeter. Here is the view of a spectrum in 1000 to 1500 angstrom region, and after calibration we achieve a wavelength uncertainty of 0.005 angstrom. So here is the energy level diagram of AU4. Its ground configuration is 48 and the excited configuration is D76S and D76P. These two transition arrays are allowed, but the transition among these levels as well as this interconfiguration transitions are forbidden. So we established the energy levels of all the levels involved for these configuration. Since the energy levels of the D8 configuration and D76s are known, we can accurately predict forbidden transition between them. So here is the transition probabilities event type that computed for the AU4 spectrum using HFR and HFR plus colpolarization approach method. So here I have compared these two results after converting the corresponding AU values into the Einstein. So the comparisons are made according to the absolute value of the S. So here are the accuracy of these transition depending upon their S values. Since we have calculated the transition probabilities for forbidden lines of U4 using three set of theoretical models, HFR, HFR plus C-pole, and a fully relativistic multi-configuration thereafter approach. The results are compared to estimate the accuracy of transition probabilities computed by these codes. So here is the summary of the comparison as of the previous one. And finally, about the ongoing work. So here I have listed all spectra that are under our consideration. And thanks for your attention.